All right, diving in today, folks, we're tackling something really at the forefront, I think, of where machine learning is going, especially as we're building these increasingly intricate agentic AI systems.
Yeah.
And it's the fundamental question of, how can we actually get a solid grasp on, are they truly performing as we expect them to? And, how can we then effectively guide their improvement?
Yeah.
We hear a lot about these agents now that can do complex planning and collaborate and, all this stuff. But if we don't have ways to truly evaluate them and then, figure out how to make them better, it kind of feels like we're missing a piece of the puzzle.
Yeah, that's really it. We're going to be diving into a paper that directly confronts this and goes beyond the ways we've been doing AI assessment, traditionally.
Okay.
I think it's helpful to think of it like imagine trying to judge a really top-notch research group, one that collaborates a lot. If you only look at their final publication, you miss, the dynamics of how they got there, who contributed what, all that kind of stuff.
Right.
And so this is really championing a more insightful, nuanced approach to multi-agent systems.
Okay, so let's break that down a little bit more. What is the core problem that this paper is really trying to address?
So the central argument is that the very nature of agentic AI, the fact that it tends to be non-deterministic, right? Meaning it can do things differently, even with the same input. Its reliance on context and the fact that it's always sort of evolving in the way it works means that our traditional black box methods, where we just, give it an input, see what the output is and judge it that way, just doesn't cut it.
Okay, yeah, that makes sense. It's like, it's not enough to just see the finished product. You got to kind of understand the process and how they got there.
Yeah.
So if we keep doing it this way, if we keep looking only at, did it pass the test or, whatever that metric is, what are we really missing out on?
You're missing out on a lot. We're losing the ability to really debug effectively, to see where the inefficiencies might be, to understand how these agents could be interacting better, and crucially, to diagnose those root causes of failures.
Yeah.
The paper really dives into two critical challenges that highlight why we need this new evaluation paradigm.
Okay.
The first one is something they call flow variability. So think about it this way. Even if you give the exact same input to an agentic system multiple times, it might actually take quite different paths each time to get to the result. And that's because, you've got these LLMs that are powering them. They're inherently probabilistic.
Right.
And then you have the dynamic dependencies between the agents themselves.
Okay.
So it creates this inherent variability. And it's not just a theoretical concern. They did a user study with practitioners, and a massive 79% said that this non-deterministic flow was a major obstacle in their work.
Wow. So like 4 out of 5 people are saying that this is a huge pain point for them. So same input, potentially drastically different internal process each time.
Yeah.
It sounds like, if you're trying to make sure it works reliably, or if something goes wrong, you have to track it down. It just makes it incredibly complicated.
Exactly.
So what's the second challenge?
The second one is natural language variability. And this is really about how language works, right?
Yeah.
So these systems, they use natural language to get instructions, to talk amongst themselves, all that. And the thing is, even tiny changes in wording or context can lead to very different interpretations by the AI. And of course, if the AI interprets things differently, it's going to get different outcomes. So it's like the inherent ambiguity of language itself is kind of amplified because you're working with these multi-agent systems that are, complex.
Yeah, it's adding this extra layer of complexity and kind of unpredictability because, language is messy. Okay, so to make this really concrete, the paper dives into a specific example, and I think it's a calculator example, right?
That's right. They use this calculator agentic system to really show these challenges in action.
Okay.
And it's not your typical, 4-function calculator. It can handle regular math, but also natural language inputs.
Oh, okay.
So think like nested calculations, or if you were to say, hey, find the average of these numbers,
Okay.
It can also do parallel and distributed computations.
Yeah.
And it even uses this thing called LangGraph to kind of make sure that the planning and execution steps are logically sound.
Okay, that's a lot packed into this calculator system.
Yeah.
So they built this calculator system, but they also, they didn't just theorize about it. They put it through its paces, right?
Absolutely. They ran experiments on it using 50 different examples, including both, straightforward math problems and ones expressed in natural language.
Okay.
And to really capture the variability, they ran each example 5 times. And then they looked at a bunch of different metrics, things like the accuracy, how much the execution flow changed, the cost in terms of using OpenAI's API, and how long it took to run each one.
Yeah.
And to really measure the inconsistency across those 5 runs, they used something called the coefficient of variation.
All right. So what did they actually find? I mean, was this variability as bad as they thought it might be?
Yeah, the results were pretty eye-opening. When they looked at just the pure math problems, the average coefficient of variation in the execution flow was 63%.
Wow.
Meaning, even for a simple math problem, the way the system was solving it internally could change quite a lot from one run to the next.
Wow.
Then, when they switched to natural language inputs, the accuracy had a coefficient of variation of 19%.
Okay.
Which shows that, even if the natural language is asking the same thing, you're not always guaranteed to get the same answer.
Right. So that really highlights how that ambiguity of natural language just, it adds this whole other dimension of things that can change and lead to inconsistent results. So it's interesting that they actually did a user study, because it shows, it's not just a theory, it's actually affecting people in the real world.
Exactly. And the user study, they talked to 38 practitioners, and 80% of them said that, non-deterministic execution, that's a major problem for us.
Okay.
Other big issues were agents just not following instructions, which 66% of them reported.
Oh.
And then 63% said that the agents were sometimes picking the wrong tools for the job.
Okay.
And it gets even worse. 60% said that the current analytics tools just aren't good enough to deal with these agentic systems.
Right.
And then 77% said they struggled to figure out what went wrong when something did go wrong.
Right.
So it's no surprise that a large majority, like 76%, said their top priority is to just understand how the heck these agents are actually working.
Yeah, that makes total sense. We have these powerful tools, but it's almost like we can't really see inside of them and figure out why they're doing what they're doing. So if the traditional methods are failing and the current analytics tools aren't good enough, what is it that's missing from the current approach?
So the paper argues that current methods just don't really account for the specific challenges of agentic systems.
Okay.
Like, one is this thing called context sensitivity. So how an agent acts depends a lot on the specific details of what it's been asked to do and even its past interactions, right?
Yeah.
But traditional tools, they don't always pick up on that. Then you have the fact that, when these agents are working, the output of one step heavily influences what happens next. And this can happen over time, right?
Yeah.
These interactive and temporal dependencies, those are really hard to capture with traditional methods.
Yeah.
And then, of course, you have multiple agents working together, and they're all, communicating and collaborating, and those dependencies are just really complex to model. Yeah.
So on top of all of that, you have technical challenges.
Okay.
The execution traces, the logs of what the agents are doing, they're just massive and super complicated. You have a ton of data to deal with, which makes it hard to scale.
Yeah.
And then even if you can collect all the data, you still need to make sense of it, right? You need explainability.
Yeah.
And that's a huge challenge in itself.
So their solution isn't just to get better at measuring the results. It's to fundamentally shift our focus to the process, to the internals of the system.
Exactly. They're advocating for this idea of behavioral benchmarking.
Okay.
Where instead of just looking at, did the agent get the right answer, you're actually looking at, how did it arrive at that answer? What steps did it take? What decisions did it make? How did the agents interact with each other?
Okay.
And this all ties into enhanced observability, which means having much better visibility into what's actually going on inside these systems as they're running. Okay, so that makes sense. But to do that, you kind of need to break down these systems into their core components. Right?
Yeah.
You need to understand, like, what are the building blocks of these agentic systems?
Precisely. And the paper does a really good job of laying that out. They define the core entities of agentic AI. So starting with resources.
Okay.
These are all the inputs, the outputs, any constants that the system is using.
Okay.
Then you have tools. These are the actual pieces of code that the agents can call on to do things. But it's important to note, these aren't just, regular functions that always do the same thing. They can be quite variable in how they work, what they do, all that.
Right.
Then you have workflows. These are like the dynamic blueprints for how tasks get done. They're represented as graphs that show the steps and how they're connected.
Okay.
And then the tasks themselves are the individual units of work. And of course, you have agents, which are the autonomous entities that carry out those tasks.
Yeah.
And finally, you have multi-agent organizations, which are like structured collections of agents that have different roles and ways of working together. It's kind of like a mixture of experts type of architecture.
Okay, so that's really helpful to kind of like break it down and understand the different pieces that make up these systems. So once we understand the pieces, what do we do with that? How do we actually achieve this enhanced observability that they're talking about?
So they talk about extending existing observability frameworks, things like OpenTelemetry, which is pretty widely used for monitoring regular software applications.
Okay.
But they say, hey, we need to add something specific for these GenAI agents.
Okay.
So they propose something called GenAI events, which are designed to track everything that happens to those core entities we talked about.
Okay.
So when an agent is created, when it's updated, when it starts doing something, when it finishes, and importantly, when something goes wrong. And these events, they categorize the severity of the problem, like whether it's a critical error or just a warning or some info or a debug message.
Okay.
So think of it like, really detailed timestamps with descriptions of everything the agent is doing, along with any problems it encounters and context.
Okay. Yeah.
And all this information is standardized so we can use it across different systems.
No.
And the idea is that this granular stream of data gives us a much richer picture of how these systems are actually behaving in real time.
Okay, so it's not just like, collecting logs. It's really about like tracking the entire life cycle of these agents and the tools and everything that they're doing.
Exactly. And all this data that you collect, that feeds into what they call the Agentic System Analytics taxonomy.
Okay.
So they basically categorize different ways of analyzing this data.
Okay.
First is passive analytics. This is basically just extracting insights and recommendations from the data. Like, for example, looking at the flow of tasks as a hierarchical graph with metrics like, how much it cost, how long it took, and were there any errors.
Yeah.
Then you have exploratory analytics, which is more interactive. So think like a chat interface or a dashboard where you can dig into the data, try to optimize the system, troubleshoot problems, and compare different things. And this can even be guided by LLMs or classical optimization algorithms.
Okay, so this is where you're starting to like, not just record what happened, but actually like try to figure out, okay, how can we make it better in real time?
Yeah, exactly. And then you have the third category, which is interventional analytics.
Okay.
And this is where you actually start changing the system's behavior based on what you've learned from the analytics.
Okay.
So this could be things like increasing monitoring on certain parts of the system, giving feedback to the agents to, steer them in the right direction, changing configurations, or even automatically replacing parts of the system that aren't working.
Okay, so it's going from passive observation to like active intervention.
Exactly, but there's a catch.
Okay.
They found in their user study that only 16% of practitioners really trust the system to make these changes on its own.
Right, yeah.
So there's a lot of hesitancy there, which is understandable, giving AI that much control.
Yeah, it makes sense, especially in these early stages. I think, people are understandably cautious about giving AI too much power to kind of self-correct or intervene in these complex systems. So we've talked about how to observe them, how to analyze the data, but how do we actually evaluate these analytics tools themselves?
Yeah, that's another really important point the paper makes.
Yeah.
They say, look, just like we benchmark agentic systems, we need to benchmark the tools we use to understand them. So instead of testing them with, language tasks or whatever, you test them with an execution log.
Okay.
So basically, a detailed record of everything an agent did while trying to solve a problem. And the benchmark would then see, can the analytics tool correctly figure out if the agent succeeded, if there were any problems, and if so, what those problems were.
Okay, so it's like giving the analytics tool a test, a real world scenario to try to analyze, and then how do we know if it's doing a good job? What's the reference point?
So for each execution log in the benchmark, you need ground truth.
Yeah.
Which is basically, the correct answers, the information that we know is true. And this ground truth should include a few key things. One, a structured representation of the task flow. So basically, what steps did the agent take in what order? 2, some overall metrics about how well it did. Were there any failures and what kind of failures?
Okay.
And 3, a detailed list of all the individual failures with clear descriptions of what went wrong.
Okay.
And then you compare the output of the analytics tool to this ground truth to see how well it did.
So they're not just talking about this theoretically, they're actually putting it into practice, right?
Yeah.
They created a benchmark data set for this.
Yeah, they created something called ABench,
Okay.
which stands for Agent Analytics Behavioral Benchmark.
Catchy.
And this is publicly available. It has 30 execution logs from that calculator system we talked about earlier.
Okay.
And they cover a range of scenarios, like successful calculations, natural language queries, distributed computations, and examples where the system made errors.
Okay.
And for each of those logs, they provide the ground truth, so the correct information about the task flow, the metrics, and all the failures.
So they basically created like a test suite for these analytics tools.
Yeah, exactly.
And they actually tested an existing tool against it, right?
Yeah, they looked at a system called TAMAS, which this stands for Task-Oriented Analytics for Multi-Agentic Systems.
Okay.
And this was developed by IBM. It's built on top of OpenTelemetry, and it's specifically designed to analyze multi-agent systems. So they ran TAMAS on this ABench data set, and it actually didn't catch all the failures.
Okay.
It missed some things, like some validator failures, and had trouble with logs that had, syntax errors in them.
Interesting.
Overall, TAMAS, its summary of what happened, matched the ground truth about 60% of the time.
Okay.
So it's a good start, but clearly, we need better tools.
Yeah, it highlights the need for more work in this area.
Yeah.
Okay, so this is all really interesting, and it seems like a really important step forward in understanding these agentic systems. But this work doesn't exist in a vacuum, right? It's part of a bigger picture, a historical context. So can you talk a little bit about that? Like, how did we even get to the point where we need these kinds of sophisticated evaluation methods?
Yeah, it's been a gradual process. We started with just basic text logs, right? Just, recording what was happening in the system.
Yeah.
But then software became more complex, more distributed,
Right.
and we needed better tools to keep track of everything. So that's where things like OpenTelemetry came in, right? These standardized frameworks that could collect logs, traces, and metrics in a unified way. And then the web came along. And with web applications, it's not just about the system itself, it's about how users are interacting with it.
Right.
So you needed tools that could analyze user behavior, understand these complex interactions. And, even before LLMs became mainstream, we were already seeing the need for more sophisticated analytics with AI systems, because even then they were doing things that weren't always predictable.
Yeah.
Like early chatbots, they would generate so much data from conversations, and you needed new ways to analyze those conversation patterns, figure out where they were failing, just get a better sense of how they were behaving overall.
So it's interesting because it sounds like a lot of the challenges that we're facing now with agentic AI, we kind of saw them coming in some ways from earlier generations of software and AI.
Yeah, absolutely. But then LLMs came along and things really accelerated because now you have systems that are even more complex, even more non-deterministic, and they're creating these really intricate interaction flows.
Okay.
So that's why we're seeing tools like OpenTelemetry, Langsmith, Langtrace, Langfuse.
Yeah.
These are all tools that are specifically designed to deal with the unique characteristics of LLMs. Some of them, like OpenTelemetry, they're focused on extending existing standards like OpenTelemetry to handle LLM data, while others, like Langsmith, take a more, holistic approach, looking at the whole life cycle of an LLM application. So it's a really active area of development right now.
Yeah.
And in parallel to this, the way we benchmark agentic systems is also changing. It's not just about, did the agent complete the task? It's about, how did it do it? How did it behave? What were the qualitative aspects of its performance?
Yeah.
And we're also starting to think more about how these systems will actually work in real world situations. So it's a multifaceted evolution, I would say.
Yeah, it's like everything is kind of moving forward together.
Yeah.
Okay, so to kind of bring it all together, what are the key takeaways, from this whole deep dive that we've done?
Well, I think one big takeaway is that we can't just treat these agentic AI systems like black boxes anymore.
Right.
Their complexity and the fact that they don't always behave predictably it demands that we look beyond just the final outcome. And to do that, we need to understand their internal workings. We need to see how the individual agents are interacting, how they're making decisions.
Yeah.
And that's crucial for debugging, for optimization, for really building trust in these systems. And to get that understanding, we need standardized ways of collecting data, analyzing that data, clear definitions of what we're looking at so we can compare different systems and tools.
Yeah.
And the paper also makes a really good case for why we need to benchmark the analytics tools themselves. Make sure they're actually doing what they're supposed to be doing.
Yeah.
And the A-Bench data set, that's a great resource for doing just that.
Yeah.
So I think all of this is really important for anyone who's working with agentic AI.
Yeah. So for someone out there who's, building these systems, deploying them, what does this all mean for them? Like, why should they care?
Well, the implications are pretty significant.
Okay.
Having more reliable systems, systems that are more robust, less likely to fail, and can handle a wider range of tasks.
Okay.
And by understanding the execution flow, you can really pinpoint, where are the bottlenecks? How can we make it more efficient? More efficient in terms of cost, in terms of speed, and the quality of the results.
Yeah.
And of course, you can make sure that the agents are actually following instructions, which, as we saw from that user study, is a big concern right now. And better debugging, that saves you time. It saves you money. And the ability to benchmark these analytics tools, that drives innovation. People are going to be competing to create better tools, which ultimately benefits everyone.
Right.
And think about this. More and more industries are relying on these multi-agent systems.
Yeah.
So understanding and controlling their behavior is going to be paramount. We're talking things like software development, scientific research, customer service, all these fields that are using agentic AI, they need to know that these systems are doing what they're supposed to be doing.
Yeah. So there's a lot of, kind of like potential impact here across a lot of different areas. Yeah. Okay. So now for our novel notions segment, where we like to, kind of take things a step further and explore some maybe unconventional, but potentially, interesting and fruitful research directions. And based on this paper, what are some ideas that come to mind?
So one idea that I find really intriguing is this notion of proactive anomaly detection. And the way I think about it is like behavioral fingerprinting.
Okay, yeah, that's interesting.
So imagine you have this agentic system that's doing, some complex financial forecasting. Right now, the way we monitor these systems is we basically wait for something to go wrong.
Yeah.
Like we might get an alert if there's a sudden spike in API calls or something like that.
Yeah.
But that's reactive.
Yeah.
What if instead we could develop these behavioral fingerprints for these systems?
Right.
So we would basically analyze how they typically behave under normal conditions. What are the typical execution flows? How do they usually use tools? How do the agents communicate with each other?
Yeah.
And we could then use that information to train machine learning models to detect even subtle deviations from that normal behavior.
Okay.
So we could potentially catch problems before they even happen.
Interesting. So it's almost like instead of just, treating a symptom, you're really trying to like prevent the illness from happening in the first place.
Exactly. And this idea, it's supported by the paper because while it highlights how variable these systems can be, it also shows that there are patterns, there are typical behaviors that we can learn and understand. And we can leverage all of these advances in time series anomaly detection and graph analysis to really make this happen.
Okay.
And the impact of this could be huge. We're talking about early warnings for mission critical systems.
Yeah.
Potentially saving a lot of money, preventing disruptions. But there are challenges.
Okay.
The main one is that right now our observability infrastructure just isn't quite there yet.
Right.
We don't always have the granularity of data that we need to create these really reliable behavioral fingerprints.
Okay.
And we don't always have enough historical data to work with.
Okay.
So, it's not going to happen overnight.
Yeah.
But I think, in the next few years, I'd say it's a moderate probability that this becomes a real area of active research.
Okay, that's a really interesting idea. What about another research direction? Any other kind of wild ideas that this paper sparks for you?
Yeah. So another idea that I find fascinating is this concept of explainable agency through counterfactual flow analysis.
Okay.
So imagine you have an agent that makes a decision and it turns out to be a bad decision. Right now, we can kind of look back and see, okay, what steps did it take to get to that decision?
Yeah.
But we don't always know why it chose that particular path.
Right.
Why didn't it make a different choice? So what if we could develop a system that could actually simulate alternative scenarios?
Yeah.
So you give it the actual execution path, and then it says, okay, what if the input was slightly different? What if the agent was configured differently?
Yeah.
What if different tools were available?
Okay.
And it would simulate all those scenarios and compare them to the actual outcome. And by doing that, we could pinpoint those decision points where, a different choice would have led to a better result.
So it's like playing back the game and saying, okay, if we had made this move instead of that move, how would things have turned out?
Exactly. And this really builds on the paper's point about how complex these multi-agent dependencies are and how intricate the decision-making process is. And we could actually borrow ideas from causal inference, counterfactual reasoning techniques, and apply them to these agentic systems.
Okay.
And the impact here could be huge. We could really understand why agents are doing what they're doing.
Yeah.
Which would allow us to make them better, to make them more explainable, to address any biases that might be creeping in. But of course there are challenges here.
Okay.
Simulating these alternative scenarios, it's computationally expensive.
Yeah.
And it requires really sophisticated models of how these agents behave. So I would say the probability of this becoming, a reality in the near future is somewhere between low